Okay, so today we're going to talk about how to convert a velocity versus time graph to a position versus time graph. So we know that the area under a velocity versus time graph is displacement, which again we know displacement is the net change in position. Perfect. And this is in calculus. The area under a curve is called the integral. So it's the integral of a velocity versus time graph is displacement. Perfect. So first thing I'm going to do to go ahead and change this velocity versus time graph to position versus time graph is we're going to divide the graph into sections of like different motions. So it looks like first 4 seconds, it's moving at a constant speed. We'll do that. It looks like 4 to 8 seconds. It's at rest, and then 8 to 9 seconds. Perfect. So now what I'm going to do is I'm going to answer 2 questions. So first, what direction, sorry about that, what direction is the object moving? So is it moving in the positive or negative direction? And again, I'm only going to use the velocity versus time graph to figure that out. So right here, for the first 4 seconds, it's moving 3 meters per second. So we know a positive velocity means something is moving in the positive direction. So I know it's moving in a positive direction. And then right here, we know it's at rest. So that's just going to be 0 meters per second. Right here, we know it's moving. It looks like it's a velocity of negative 6 meters per second. So that's moving in a negative direction. And then we're going to talk about how it's moving. Is it moving at a constant speed? Is it speeding up, getting faster? Is it slowing down? Or is it at rest? So this first section right here, it looks like for that full 4 seconds, it's always going 3 meters per second. So that's a constant speed. Rest is also a constant speed, but we can call rest at rest. The velocity is 0 meters per second from 4 to 8 seconds. And then the last portion from 8 to 9 seconds, it is going negative 6 meters per second, which is a constant speed. Perfect. So now what we'll do is we'll go ahead and find the area under the graph. And again, it's the area that line makes with the x-axis. So let's look at this portion right here. So I'm going to highlight the area. Okay. So for this, we have the area this, I guess, rectangle makes with the x-axis. It's 3 meters per second. And here it's 4 seconds. And if I think about it, if you go 3 meters per second for 4 seconds, so that's 3 meters per second, first second, then 6 meters per second, second, then 9 meters per second, and then 12 meters per second. So that looks like you'd go 12 meters. And the cool thing is, if we find the area of this rectangle, so the area is 3 meters per second times 4 seconds. Seconds units cancel out on the top and the bottom, so we're left with 12 meters. So the area of this rectangle is 12 meters. So that means you go 12 meters. This next little portion right here, it has no area because it's just at 0 meters per second. So you go 0 meters. Cool. Now let's look at this last little portion. So this is negative 6 is this. So it's negative 6 meters per second. And we go over 1 meter. So if I find the area, I'm going to go ahead and highlight the area. If I find the area, it's going to be negative 6 meters per second times 1 meter, or excuse me, 1 second. 1 second, and we're going to be left with negative 6 meters. Perfect. So now what we can go ahead and do is we can label our position versus time graph. So we have position, which we'll measure in meters, and then time, which will be measured in seconds. Great. So first we have to label our starting position. So in the problem, it tells us we're assuming the object starts at 1 meter. So let's go ahead and have 0. Let's go ahead and have 1 meter it starts. So we're going to start here. I'll go ahead and draw a little data point to where we start. So the first position, you're moving 12 meters in a positive direction. So from 1 meter, my displacement is 12 meters, so I have to go up 12. So if I'm going forward 12 meters, I'm going to end up at 13. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Great. So 13. So I will end up right here. Now, after I draw my starting and ending point, now I can connect the 2 points. So constant speed, we know that is represented by a constant flat straight line on a position versus time graph. So now let's look at the next part. You're at rest, so you're just staying at 13 meters for that whole entire section. So now you're at 13 meters. Our displacement is now negative 6 meters. So that means we're going to go backwards 6 from where we are. So we are at 13, so we need to go back to 7. So let's see, 12, 11, 10, 9, 8, 7, 2, 2, 2, right here. Now I'm going to go ahead and connect the points. So it's a constant speed, so it's a flat line, just like this. Perfect. So now what I'm going to do, just for practice, I think it's good to do, I'm going to go ahead and find the distance and displacement. And I would encourage you to do this on your own first. So distance for position versus time, go ahead and do that. And then let's go ahead and do it for displacement. So distance for this, it looks like we go up 12, and then we go back 6. So it looks like you're going a total of 18 meters. Now for displacement, that is our net change in position. So that's your final position minus your initial position. So our final position was 7 meters, and your initial position was 1 meter, where we started right here. So that's just going to be 6 meters. Perfect. And that is your displacement for 6 meters and distance for 18 meters. Cool. I also think it's good to do it from velocity versus time graph. So I encourage you to think about how to find the distance and displacement for velocity versus time graph. Pause this video and then come back and watch. Cool. So I bet you already figured out some cool things. But to find the total distance for a velocity versus time graph, you're just going to add up all the areas, like the absolute value of the areas, considering them to be positive, which makes sense because this negative here, it's just here to say direction. So we have 12 meters plus like the absolute value of negative 6 meters. So that's 18 meters. So the distance is 18 meters. Again, we're not worrying about signs because distance, we don't care about if we're going forwards or backwards, just that we're doing this. Now displacement, we're going to have to keep the negative directions in mind. So displacement is going to be, we have 12 and then we have negative 6. So this is going to be 12 plus negative 6. So we're going to be left with 6 meters for your displacement. Awesome.